So hope you can listen me. So let us start today's lecture. In last class, we have seen this minimum distance classifier. The idea was very simple. Say this is group 1 and this is group 2. And suppose this is some X test sample lying over here. So what we do is we find out this representative prototype for say class 1 and this second prototype for class 2, and they are actually centroids of these groups. So what we do is basically we try to find out say distance d1 from x test to x1, that is prototype 1, and say this distance d2, and we say if d1 is less than d2, class of x test is class 1. d2 is greater than d1, then class is 2. Am I right? This should be d2 is less than d1. So whichever cluster or group is near to the unknown sample, we assign that label to the given sample. So that is very simple trick. Now, question arises when d1 is equal to d2, what will be your decision? Say for example some sample is somewhere here. So this distance d1 and this distance d2 is same. So we cannot actually decide. So this will be the decision boundary. So all the samples which belong to such thing, that is d1 is equal to d2, then really you cannot decide. So if you find out all those points and join, then you will get certain line like this, which will pass through the midpoint between the centroids of two groups. Okay, so this will be some xp, and it will be perpendicular to the line joining x1 and x2. So throughout this line, d1 is equal to d2. So any sample which is on this line, anywhere on this line, will satisfy the condition d1 is equal to d2. That means you cannot classify these points. But when you're above this line, that is d1 is less than d2, and you are below, that means d2 is less than d1, then you can easily decide the category. So this side of the line becomes class 2 and this side of the line becomes class 1. Now question is how to find out this line equation decision surface from the given sample. So then we can see the small derivation based on the distance itself. So yesterday we saw this and we find out this as our discriminant function or the decision line. So what is x1? x1 is prototype of class 1. x2 is prototype of class 2. So first of all, from data we will calculate these two things, x1 and x2. Once x1 and x2 is calculated, you can easily find out x1 transpose x1, which will be equal to norm of x1 square. So this quantity. Similarly, you take x2 vector, transpose it, multiply with itself, it will give you norm of x2 square. So which is required here. So it's very simple. From data you have to just compute centroid for, I can write here centroid for each group. So once you do that, you can easily find out this decision surface. Now you can represent this with the help of this hyperplane equation, w1 x1 plus w2 x2 and so on up to wn xn plus wn plus 1. So there is no variable here. So this is a constant term. Now if you look at this equation, so this is my space variable x, which consists of all the variables, that is x1 to xn. So this is nothing but a vector x1 x2 up to xn. And what is this? This is vector minus another vector. So this will be a vector. So it will be a vector with some numbers. And these numbers, I am calling it as w1, w2 and so on up to wn. So this I can write as w transpose x. So this first term in this equation, I can call it as w transpose x. Now plus the second term. If you observe the second term, there is no space variable here. No space variable. There is no space variable involved. x1 norm square and x2 norm square, they are some numbers. So it's a length of the vector, so they are numbers, and number minus a number is again a number. So this is a constant. So this constant I am calling it as wn plus 1. So for each space variable x1, x2 up to xn, the associated numbers are suppose called as w1, w2 up to wn. So if I collect these variables, then it becomes a w vector, and if I collect all space variables, it is a space variable vector. So these two things multiplied together will give you this part of the equation and plus the constant term. Now I can write this equation in this form, where I can write this w here, say this is a w, this one, and the extra term, that is wn plus 1, which is here. So I augment the w vector by one term, that is wn plus 1. So this is called as augmentation, where the original vector w is added with some other number. So the dimension is increasing from, say, n dimension to n plus 1. So this will be a vector with variables n plus 1. Now, to have this product properly, what we have to do is we have to transpose this, and we have to take the space variables x and suffix with 1, so that the dimensions are now matching. So this x vector is n dimensional, and I am adding one more dimension. So this will be n plus 1, and this is also n plus 1. Now the product can happen between these two vectors, and this is equal to 0. So this will give you another form of the same equation. Suppose I call it this as A. This equation number A can be written in vector forms in two ways. The first one is W transpose X. This one, this is first way. W, same, I can write this equation A in two ways. First way is W transpose X plus Wn plus 1 equal to 0, this one. And if I take this Wn plus 1 in this W vector and I extend that, then this will be extended version of that W vector. Okay, so called as augmented weight space. Actually, neural networks, we call it as augmented weight space. And this X, the space variable, collected together. So all these variables, if I collect together, you will see that there is no variable here, but I can take this as 1. Okay, so this is multiplied by 1, so there is no harm in that. So this dimension, if I collect for all of them, then this is X and suffixed with 1. So this will be augmented space variable. So combined together, you will get the same equation as 1. So there is no actually change, but there is a rearrangement of the terms. So that's the only thing we are doing here. But this second equation is helpful when we want to see the things in weight space or this W space. We will see these things when I will tell you the perceptron learning in detail. So this will come again there. Right now, just see that this equation we can write in these two forms. So this is augmented form and this is the normal form. Now here you have to see that W is computed like this. It's a difference between two vectors. X1 is your prototype for class 1, X2 is prototype for class 2. And Wn plus 1 term, that is a constant term, is a difference of two norms, that is X1 norm subtracted from X2 norm square. So let us take one simple example and try to design a dichotomizer. So your problem is design a dichotomizer from given data. So data is like this. We have class 1 samples. You are provided 3 samples here. Class 2, you are provided again 3 samples. So this is not restricted only for 3 samples. You can take as many samples as you want. So, but for the sake of simplicity, I am taking only 3 samples. And question is design a dichotomizer. Now, what is first step? First step is to find out centroids or prototypes. Now let us calculate, suppose x1. So how it is calculated? X1 is equal to, you take all the samples which are belonging to class 1. Okay, suppose I write here x1, then you take the first dimension of each sample. So 1 plus 1 plus 2 divided by how many samples? 3. And then 1 plus 2 plus 1.5 divided by again 3. Then you calculate second prototype. You take group 2 now. You take first dimension, that is 5 plus 5 plus 6 divided by 3. Then you take 1 plus 2 plus 2 divided by 3. Okay, so this is very simple prototype calculation. So if you solve this, you will get two prototypes. X1 is equal to this 1.3 comma 1.5, and X2 is 5.3 and 1.6. So we have now two prototypes ready. So this will represent class 1 and this will represent class 2. What we have done, we have just found out the mean of the respective classes. Now I can write actually this in vector form. X1 is equal to 1.3, 1.5. I should write actually like this. Then X2 is 5.3 and 1.6. Now our half work is done. Then we have to use the formula that we have derived already to compute the W vector. Now W vector is what? It is x1 minus x2. Okay, so that you can find out here. So W is 1.3, 1.5 minus 5.3, 1.6. So that is minus 4 minus 0.1. So that you keep aside, and then you calculate this constant. So this constant is nothing but norm of individual vectors. So x2 norm actually is what? X2 norm is square root of its length. So what is x2? So x2 is 5.3 square plus 1.6 square. And what is x1 norm? X1 norm is length of that first vector, x1 vector. It is 1.3 square plus 1.5 square. But what we want is norm square. So just square it. So this will go. Okay. And then you take the subtraction and multiply it by 0.5. So if you do that, you will get Wn plus 1. So Wn plus 1 in our case is 13.35, and W was calculated as minus 4 and minus 0.1. So our design is now ready. So dichotomizer is now ready, and the decision boundary is given by this W vector multiplied by the space variables. So I will call it as X plus this constant W n plus 1. So if you multiply this, or if you want to write in the form of equation, then this is our decision boundary. Okay, so now suppose I want to write the same thing in terms of the augmented weight space. Then what we can do is we can write this as minus 4, minus 0.1 and 13.35. What we have to do? We have to take the Wn plus 1 and write over here. So this transpose multiplied by x1, x2 suffixed with 1. That's it. Now if you multiply these two things, again you will land to same equation. But this is called as augmented weight space representation. Okay. Now given this line equation, in this case, if you plot this, it will look like this. Okay, so this is my decision line, I have divided this space now into two halves. This side of the line is class 2 and this side of the line is class 1. So if I call this line as my discriminant function, I can call this as g of x is equal to minus 4x1 minus 0.1 x2 plus 13.35. If I call this as my discriminant function, so what I have to do is I have to supply input x, and this will go to this g of x, and I have to take a decision. If my output is positive, I will declare it as class 1. If my output is negative, I will declare it as class 2. So why I am doing like this? We will take some example. Suppose x test, the sample I want to test, suppose is 1 1. So this sample, if you go to the training data, this is the first sample. It is 1 1 is the first training sample. I know that it belongs to class 1. Now let us see whether this is coming or not. Okay, so what we have to do is we have to take this g of x is equal to our equation and substitute there in this equation value of x test. What is x test? X test is 1 1. And if I write this properly, this is minus 4, I think x1. So where is this? This is minus 4 x1 minus 0.1 x2 plus 13.35. So this is my g of x. Now what we have to do is we have to substitute this 1 1, the given sample, here. So 1 will go here and this other one will go here. So this will be 4 into minus 4 into 1 minus 0.1 into 1 plus 13.35. So if you solve this, your answer is positive. So if once your answer is positive, you will declare this as your class 1 sample. And we know that 1 1 was actually belonging to class 1. So our dichotomizer is working fine. Now we can take another example, 5 1. So if you go to our data, 5 1 actually belongs to class 2. So let us see what happens. Now substitute in this equation again the value 5 and 1. So I am writing here 5 and 1 and solve this. So you will get again number minus 6.75. So minus 6.75 is a negative number. So I will declare it as class 2. So now let us take some unknown sample which is not there in our data set, say like 0 0. I don't know to which class it belongs actually. I was knowing about this 5 1 because it was my training sample. I was already knowing this. I was just checking whether our system is working on training samples correctly. Now I am confident that it is working on training samples correctly. Then I can deploy this system in actual use and I can use it for some purpose. Now, if suppose some unknown measurement appears to you as 0 0, what happens? So I have to put now in place of x1 and x2, in place of x1 and x2 this here as 0 0, and then the constant will be there 13.35. So answer is positive, so I will declare this as class 1. Okay, so the input 0 0 now belongs to class 1. So this is my decision. So we can go to the diagram. So this diagram, and this was the test point that was given to us, that is 0, 0, and we have decided this belongs to class 1. So you can check now. This was my decision boundary, and we said that this side is positive side of the line and this side is negative side of the line, and whenever any sample which belongs to this side, I will declare it as class 1. Now remember forever a simple thing, how to if somebody gives you a line equation and some equation, maybe 1, say x1 plus x2 plus 5 equal to 0, or any other equation, minus 3x1 plus 5x2 plus 8 equal to 0, or minus 3x1 minus 8x2 minus 10 equal to 0. So there are three, suppose, equations, line equations given to you. So you can plot these line equations on x1, x2 plane, and then if I take this equation as a function, say if I call this as g of x, x1 plus x2 plus 5, what happens is only on this decision line or only on this line, the function value is 0. So function value is 0 on this line. Okay, it will be greater than 0 in one side of the line and less than 0 on the other side of the line. So here I am saying this side is positive, this side is negative. On this line it is 0. Okay, now how to see or how to find out which side of the line is positive, which side of the line is negative for a given line. Suppose I take this first line, number 1, and substitute 0, 0 in this line equation, then I will get 5. That means 0, 0 belongs to positive side of the line. Okay, like that I have to check. Now a simple way to do this is to collect the coefficients of the line. Suppose I take this 1, 1. Okay, then this is the vector which is pointing the positive side of the line. It's like that. Okay, now if I take our equation, say this one, the current problem equation, and collect the coefficients of the line variables, which is minus 4 and minus 0.1. Try to plot this vector, say somewhere it will be, say, minus 4 here. Suppose this is minus 4 and minus 0.1. Say maybe somewhere here. So this is the direction of this vector. Now this is the positive direction. So if you extend this vector, then you will see that this side of the line is positive and the opposite side of the line is negative on the line function g of x is equal to 0. So this becomes our idea, and this idea we are going to extend in perceptron learning rule. Perceptron is doing same thing. It is implementing a line. It will give you answer plus 1 if you are on the side of the line where g of x is positive. It will give you negative answer if you are on the other side of the line. So you can do a job of class 1 oblique class 2 very easily using a line. So this previous example demonstrates how minimum distance principle actually implements a dichotomizer. So the basic principle behind the dichotomizer or a classifier is the minimum distance. Now it can solve a two-class problem very easily. Question is, can we solve multi-class problem? Can we extend this for many classes? The answer is yes, we can do that. Now assume that k number of classes are to be learned, and we are going to use Euclidean distance metric to measure the distance between two samples. Now instead of two prototypes, in earlier problem we have x1 and x2 as our prototypes. Now in this case, since I want to learn k classes, I have to find out k number of prototypes. That's it. Okay. Now the distance between, suppose, first prototype and the given test sample is equal to the norm of the difference vector, that is xt minus x1. Okay, say this is x1 prototype, this is some x test, and I want to find out this distance. So this distance is xt minus x1 norm of that. Now this you can easily write as xt minus x1 transpose xt minus x1. So this will be norm square. So this will be norm square. I can write this as xt minus x1 norm square, and actually I want distance, so I will take square root of that. So this will be d1. Then you can find out d2 in similar way, that is xt, that is your test sample minus 2. So xt is your fixed thing, that is this is the test sample, and then minus x2, that is prototype, and norm square. You can see here I am taking now distance square. So there is no harm in taking square of the distance. Unnecessarily this square root thing will come into picture if I take simple distance. So if I take distance square, the calculation of this distance, that is square root, you can avoid. Okay, so simple thing is you just take square of the distances, so this square root will go away. So you will do this procedure for all the samples, all the prototypes, that is from x1 to xk. So the corresponding distances are d1 to dk square. Now for some ith prototype, for a intermediate some ith prototype, distance square is equal to xt minus x1 transpose multiplied by xt minus x1. So if you expand this, you will get a multiplication like this, xt transpose. So this xt transpose you will multiply here, then xt transpose you will multiply here, then xi transpose you will multiply here, then xi transpose you will multiply here. So you will get 4 terms like this. Okay, so you can club these 2 terms because they are same things. So it will be xt transpose xt minus 2 into xi transpose xt plus xi transpose xi. Now this is my di square, where I is ranging from 1 to k, because I want to learn k classes. Now what procedure I will take to take a decision is to find out which is the minimum distance amongst d1, d2 up to dk square. Okay, so you have to find out who is producing minimum distance square. So that is suppose some jth class or jth index of this, then we can declare that as the class of given input. So what is simple idea here? We are extending 2 class problem to k class problem. So this is my x test. I have some prototype x1, some x2 here, maybe xk here. So I will calculate distance d1 with this, d2 with this, and so on up to dk. So since this distance is suppose minimum amongst the k prototypes, that is x1 to xk, d2 is suppose the minimum distance square, then we will declare that x test belongs to class 2. So whichever is minimum, that will be declared as the class. So this is the simple idea and its extension from say 2 class to k classes. So you can club this thing, that is xt transpose xt minus 2 into xi transpose xt plus this is our distance square, and now I am calling it as discriminant function for ith class. Okay, so now I am saying that my discriminant function for dith class will be equal to, or this gith class will be equal to di square. So for ith class I have to design gix, and that I am saying I will take it as di square, that is distance of input prototype from ith prototype. So di square that we have seen in last slide, now I will call it as gix. Okay, now this, if I take this 2 out, okay, so this will be multiplied by half, this minus sign will go inside, and I can write this in this form. Now if you observe closely, you will see that the first term is a constant. It won't change for a given test sample. This is a fixed number. Now why I am saying, because x test is suppose 1, 2, x test transpose x test will be 1, 2 multiplied by 1, 2. So this will be 1 plus 4, that is 5. So this 5 is fixed for a given x test. Now what is varying is the variable is I. It will range from I equal to 1 to capital K. So if I say x1, then it is taking prototype number 1. If I say I equal to 2, it will take second prototype. If I say I equal to k, then it will take kth prototype. And what is our idea? We are searching for minimum distance. Okay, and if I say this part is fixed for a given sample, it won't change, then which function will give you minimum? The function which has maximum value of the second portion of this equation will give you a minimum distance. For example, suppose I say 100 minus 5, and the other equation, suppose I say this is g1x and g2x is 100 minus 25. So this will be 95 and this will be 75. So this will win because I am interested in minimum. But if you compare these two things, I have selected actually max of this. Since this is fixed number, when difference will be minimum? When the second term is maximum. So what I can do is I can throw this first calculation here. I can drop this term. So we are going to drop this. And we are just taking this part, second part. And I will call that as some GI x dash. And I will take this as now discriminant function. Instead of distance square, now I am saying that I will choose this as my activation function, discriminant function. And instead of minimizing, I will now go for maximization. Okay, I will go for maximization. I will search for maximum value of GI x dash instead of minimum value. Here, if I use this quantity, full equation, then I am in search of minimum. But since this is a fixed number and I am searching for minimum distance, I have to maximize this portion of my calculation. So why to calculate this? Because this is a repeated thing. So I can drop this, I can throw this, and I just calculate here the remaining portion of my equation, and I will search for now maximum value. So we have now some g1x, g2x, and so on up to gkx. So some k functions, they will receive same input, that is x, and then we will search for a maximum value of these functions. So tomorrow we will see, or in next class actually on Thursday, we will see one problem based on this. So let us stop now.